Hello everyone. So in this video we're going to visit how we can solve transcendental equations with perturbation approaches. And in this video, more precisely, we're going to tackle a transcendental equation involving a trigonometric function because we're going to solve x times the tangent of x is equal to something large, all right? Epsilon, as usual, is a small number, and we would like to derive an asymptotic expansion for the roots of that equation. As we will see, this is a little bit more difficult than what we used to see with the simple algebraic equations, but yet this is not impossible to find solutions to those equations. All right, so before delving into such a problem, I would just highly recommend to have a clear picture of what you're looking for. And so here, in particular, we see that the function we want to solve is x tangent of x is equal to something large, right? So something large has been just illustrated here as just drawing a line over here quite high. All right, this one is supposed to be representative of 1 over epsilon. And so you see that I chose here an ordinate of 20, meaning that epsilon in this case would be equal to 5%. Okay, that's typically what we mean when we have a small number. If it's even smaller, that's even much better for the asymptotic expansions that we derive. All right, but then what do we need to look at? The left-hand side, okay? We need to look at x tangent of x and see when this function actually intersects this very high level line. And so just to refresh minds, I have plotted here the tangent of x with orange curves, orange lines. And you see that this is a periodic function, all right? It just comes with the exact very same shape, and just repeats itself with a period of pi. And the tangent of x is known to have asymptotes at pi over 2 plus integer multiples of pi, all right? So And this is, of course, where the function tangent of x is very large. And so you see that when you multiply this by x in the neighborhood of the origin, so for small values of x, you see here that we have small values of x going to 20, meaning that we have 1, 2, 3, 4, 5, 6 periods for the tangent function here. Well, in fact, you see that we do not really change the crossing point with respect to where it would be if we would have just considered tangent of x is equal to 1 over epsilon. But then you see that it starts drifting quite significantly as you go further and further to higher roots. And if you go to very high roots, then in fact you see that the multiplication of the tangent of x by x is such that this function here gets steeper and steeper. And if you go a little bit further away, then in fact you just realize that you multiply by x, this multiplication by x creates something that is in fact really steep. And the intersections that we were expecting to be at pi over 2 plus integer multiples of pi, actually we see that they are shifted and they appear to come at integer multiples of pi, all right? So this is the behavior we would like to capture. So definitely we see that in the discussion here, we have identified two things: small roots and large roots. And definitely large roots. For each of them, we'll have to have a different approach, and we will end up with different asymptotic expansions. All right, so let's start with small roots first and see what we can do with the small roots. All right, so what we can start with is just by considering that when we write x tangent of x, we want something large, so which is of order 1 over epsilon. And we said that for the small roots, actually, the tangent of x is a quantity that is large. All right, so we can find a sort of balance between the different orders of magnitude in this problem just by saying that x shouldn't be too large, tangent of x is large and has the same order of magnitude as the right-hand side, which is 1 over epsilon. All right, so if we do this, then of course the natural approach is to seek solutions in the neighborhood of the singularity, seek solutions in neighborhood of the singularity. So this is where tangent of x is large, which means pi over 2 plus integer multiples of pi. All right, so for this we can write an ansatz. That's probably kind of a naive approach, but you will see it doesn't work too bad. And say, let's try to use something like pi over 2 plus k pi plus small perturbations around those values. So I'm going to write a sequence as we would typically do. So epsilon times x1, epsilon squared times x2, and so on. All right, what we need to do now is to substitute this into the governing equation. All right, so but we don't know, as you noticed right on, we don't like to deal with epsilon in the denominator, so we're going to push this on the left-hand side. All right, so the governing equation is epsilon multiplied by pi over 2 plus k pi plus epsilon x1, epsilon squared x2, and so on, multiplied by the tangent of x, and this is equal to 1. All right. So what do we do when we have a problem like this? We need to find a balance between the different orders of magnitude, right? And we see that when we write this, of course, we are slightly stuck because on the left, we have something which is of order epsilon or even probably smaller. This is, well, in fact, what this says explicitly. And on the right, we have something which is of order 1. All right, so this apparently is something that we cannot fulfill. But in fact, we know that we are looking for solutions such that the tangent of x is something large. All right, so we should write explicitly that the tangent of x is large. And an option that we found and that we explored already in exponential functions, or even you could use this approach in other nonlinear functions, is to expand tangent of x in the neighborhood of x, right? So tangent of x, if I just replace it by its expression, we have tangent of pi over 2 plus k pi plus epsilon x1, epsilon squared x2, and so on. All right, so this is something like the function f of x0 plus epsilon x1, epsilon squared x2, and so on. And what I'm just telling you now is that we can replace this by f of x0 plus first derivative at x0 multiplied by epsilon x1, and so on and so on. So this is a series expansion of x when epsilon is a small number. All right, so we could be tempted to do something like this, but watch out. If we just replace the argument of the tangent by this x0 here, you see that we end up just by hitting exactly the singularity, right? So tangent of pi over 2 plus k pi is exactly where in the tangent of x where we have this singular behavior. All right, so there's no way, and I can just write it this way just to make sure you don't forget that's something we can't do. Pi over 2 plus k pi plus epsilon x1. We can't write this tangent of pi over 2 plus k pi plus epsilon x1 times a derivative, all right? And this is prohibited, of course, because tangent of pi over 2 plus k pi does not exist. All right, so, or if you want, we can say that this tends to infinity, or this is equal to infinity somehow, although this is something that is strange to write. All right, so we can do many things with infinity. With large and small numbers, we can play with that a little bit in the context of perturbation techniques, but definitely expanding a function in the neighborhood of infinity is something, of a singularity, is something that we cannot do. All right, so we need to find another way to make sure we can expand the problem. All right, so let's come back to our equation, and let's try to find another way to make sure this can be written in a regular manner. And so, well, definitely you understand that the singularity, and this is actually the approach, the way you should think of the problem here, the singularity here in the tangent of x, where does it come from? Because simply the tangent of x is the sine over the cosine, and the cosine of x is equal to 0 at this singular point. All right, so if we want to avoid this singularity, what can we do? Well, just multiply this equation here, left and right, by the cosine of x. All right, so it means that we would solve epsilon times pi over 2 plus k pi. I'm going to truncate at order epsilon square. Okay, so I don't want to keep epsilon square here in this term, because I already have an epsilon over there, multiplied by the sine of x, which is pi over 2 plus k pi plus epsilon x1, and so on. And this is equal to the cosine of pi over 2 plus k pi plus epsilon x1. And we have extra terms of order epsilon squared that have been dropped. All right, so, and you see that this is not a problem, this is not a problematic equation any longer. This is not a problematic equation any longer because we don't have to expand anything in the neighborhood of a singularity. All right. So what can we do next? We can just derive approximate solutions for this. All right, so this is the sign of a sum. So if you just remember that sign of alpha plus beta is sine cos plus cos sine. And if you now consider that beta over here is a small number, we'll end up with sine of pi over 2 plus k pi multiplied by the cosine of epsilon x1 plus the cosine of pi over 2 plus k pi times the sine of epsilon x1. All right, so let me just rewrite over here, pi over 2 plus k pi plus epsilon x1, which is, by the way, already of order 2, but let's keep it, it's maybe not a big deal. Then what do we have here? The sine of pi over 2 plus k pi, this is minus 1 to the power k, multiplied by the cosine of epsilon x1. This is 1 minus something of order epsilon squared, so I'm just going to drop it. So this is 1. And then we have plus the cosine of pi over 2 plus k pi. This is 0, so this actually vanishes, times the sine. All right, so this is what we have on the left-hand side. And on the right-hand side, we can do the same operation here. Just remember that the cosine of alpha plus beta is this cosine of alpha, cosine of beta, minus sine alpha and sine beta. All right, so for this expression here, we'll end up with a cosine of pi over 2 plus k pi times the cosine of epsilon x1 minus sine pi over 2 plus k pi and the sine of epsilon x1. All right, so then let's just simplify this expression to see what we have on the right-hand side. So the cosine here, we said this is 0. This is minus 1 to the power k. So we have minus 1 to the power k. And this is multiplied by epsilon x1 plus terms, in fact, of order epsilon to the third, which is something I can definitely keep as we have something already of order epsilon square on the left. All right. Good. And then what does it mean? Well, now we can just keep going. We can simplify. So minus 1, and then what do we have at leading order? You see that the leading order is in epsilon because I have multiplied everything by epsilon earlier. So we can basically simplify out by epsilon, and we find out that x1 is equal to minus pi over 2 plus k pi. All right. And so what do we have at the end? If we just now put the different contributions all together, we see, in fact, that this is also minus x0. If we observe that what comes in the parentheses over there is, in fact, nothing but our x0. So if we put everything back together, it means that the small root is x is pi over 2 plus k pi, so that's leading order, plus epsilon times x1, which means 1 minus epsilon here. All right, done, so we got it. And so it just means that based on the singularity in the tangent function, what we obtain here is just a small shift to the left. And that's what we observe here. The order of magnitude of this shift to the left of the root is something that we could determine. And the quantity by which this is shifted is exactly equal to epsilon times x1. Okay, in absolute value, it's a shift to the left. This is pi over 2 plus k pi multiplied by epsilon. All right, and remember we discussed earlier the asymptoticity of a series. In order to make sure that this sequence remain asymptotic, we need to make sure that the different terms are smaller than the previous ones. And this is something we did. We obtain in the formulation that we have over here. However, we see that the shift, as k grows large and larger, the shift can become something quite significant. All right, and so at some point, when the shift will be such that this shift has order of magnitude, let's say, I don't know, probably pi over 2, this solution won't be valid any longer. And this is why we need to go to the large roots. All right, so let's have a look now at the large roots. If we want to have a look at the large roots, probably we can just reconsider the sort of balance that we decided to consider to start with. Okay, so instead of that, we could write x tangent of x is 1 over epsilon. And we could say this time that probably, let's just swap the roles and say that x is large because we're looking for large roots. And the tangent of x is something that is of order 1. I don't want to mean this is close to 0, this is very small. I just want to say that the tangent of x is something that is not very large. All right, and so if you want to do that, probably the best thing to do is to use a rescaling as usual. So we would rescale and determine a new quantity, which is x tilde. All right, so that x is x tilde over epsilon, and this x tilde is something that is of order 1. All right, and because we use a rescaling, it should be different from 0. All right, so it means that the problem we solve is now x tilde over epsilon multiplied by the tangent of x tilde over epsilon is equal to 1 over epsilon, or just put it differently, x tilde times the tangent of x tilde over epsilon is equal to 1. And that's what we need to solve. Problem is not badly posed, as you can notice, right? This is of order 1, this is of order 1, and this is also of order 1. This is what we stated earlier. All right, so it means that we are kind of in a good position in order to solve that. However, you see that we still have here x tilde over epsilon coming in the argument of the tangent. And there's no way, again, that we could expand this as we expanded, for instance, the sine and the cosine a little bit earlier. All right, so in order to solve that problem, we can just define this, we can define it as a new quantity. And especially this works quite well when we have trigonometric equations. All right, let me just call it t tilde. And instead of seeking just one series or one sequence and solve the problem just for x, I will consider actually that there are two sequences. All right, so I'm just going to write that t tilde is t0 plus epsilon t1 tilde plus epsilon square t2 tilde, and so on and so on. And at the same time, I will use a sequence for x and say that x is x0, epsilon x1, epsilon square x2, and so forth. All right. So what we did is that we moved the problem, which was a problem with only one unknown, into a problem with two unknowns. All right. Two unknowns because we have x and t as unknown. That's the first equation we have. This is the governing equation, if you want, or this is the original problem that we need to solve. And the second equation we have is actually nothing but that equation here, which can be rewritten in a different manner. I can just write that x tilde over epsilon is the arctangent. X tilde over epsilon is the arctangent of t tilde, all right? And because the arctangent is such that we have a k pi to be added, this is the arctangent of t tilde. So we have a set of two equations, and we have two unknowns, and we have, for each of them, we have a sequence, all right? So this should be okay. We can start with the first one, and then we'll look at the second one just after. The first one, what does it say? It says that x0 tilde, I'm going to truncate early enough because I just want to show you here how it works. We're not interested in keeping so many terms. t0 plus epsilon t1 plus etc. is equal to 1. All right, so we have x0 tilde t0 tilde plus epsilon x0 t1 x1 t0, and this is equal to 1 plus terms that are of order epsilon square. All right, so at leading, we have x0 t0 is equal to 1, and the first correction says x0 t1 plus x1 t0 is equal to 0. All right, that's what we have. So we already have two equations at leading, one equation at leading with two unknowns, but I do expect that the leading expansion of the other equation will provide me would provide with us a second equation here involving x0 and t0, and I will just have to solve these two equations to get x0 and t0. Then you see that in the following equation, there are two additional unknowns, x1, t1, but I do expect that the first correction to the second equation will provide also another equation for x1 and t1, and these can be solved all together. All right, so let's keep going and expand the second equation. So the second equation just says that we have x tilde over epsilon. Let me just multiply it by epsilon, all right, because we don't like having epsilon in the denominator. So let me just multiply this by epsilon, and we have x tilde on the left, which is x0 plus epsilon x1, etc., is equal to k pi epsilon plus epsilon times the arc tangent of t tilde. All right, like this. In this case, even though this is an arc tangent, we don't have any singularity issue as we did before, right? Because remember, the arc tangent function is just the reciprocal of the tangent function, and is something that looks like this, pi over 2 and minus pi over 2. All right, so there's definitely no singularity out there, and we can expand this in the neighborhood of t0 tilde, which is something we said which is of order 1. It could be even smaller, and if it was close to 0, there's no problem. We can expand locally and find a local approximation to that function, right? So your arctangent of t0 plus epsilon t1 tilde, we can use for this Taylor series approximation, and this will provide the arctangent of t0 tilde plus epsilon t1 tilde multiplied by the first derivative of the arctangent evaluated at t0 tilde. So this is 1 over 1 plus t0 tilde square, and then we have additionally terms of order epsilon square. All right, so let's just try to summarize this. We have on the left x0 plus epsilon x1. Then on the right, we have k pi epsilon plus epsilon times the arctangent. So we have epsilon arctangent of t0. And actually already remaining terms are of order epsilon square. Okay, so what do you observe here? We need a leading. And we need the first correction, right? We're going to write the equations like this. Okay, what do we observe here is that the leading, if we just don't pay attention, we would be tempted to write this is x0 is equal to 0. All right, this is wrong, right? Because we said we have a rescaling, and with x0 is equal to 0, it means that the sequence here would start with a 0, would start with epsilon. This epsilon would simplify out with the epsilon over here, and we don't have any rescaling at all. All right. So there might be something different. And this is something really specific to transcendental equations, and especially trigonometric equations. Because you see on the right-hand side, we have this. And this actually, what does it do? It just positions x on the real axis. And it just says, okay, we have the arctangent of something on the right over here. And the arctangent, you see, at most, this is pi over 2. So at most, this is a small number, pi over 2 times epsilon. But we wanted to say that x tilde, remember, we wanted to say that x tilde could be something large, All right, so we're looking for the large roots. I just said 1 over epsilon to start, but this is something that could be even larger than 1 over epsilon. And what we observe here is that, in fact, we need for x0 tilde, we need to make sure that it match the order of magnitude, the order of magnitude of k pi over epsilon. All right, so this k that we have introduced here was something that was totally general. We haven't made any assumption on k yet. But what we need to say now is that k over here is large. And this is why actually we can't really capture the small roots with this approach. And the way to say that k is large, well, is just to make sure that k pi epsilon matches the order of magnitude of x0 tilde, which is of order 1. So we should have something of order 1 over there. And to do this, we introduce a rescaling again. Okay, rescaling. And what is just beautiful in the approach is that this comes naturally as you go through the different equations. And the rescaling would just say, okay, let's define a k tilde, which will be of order 1. And let's define it as k times epsilon. All right. So it means that at leading order, we have x0 tilde is equal to pi times k tilde. And that's the leading order. That's the leading order solution. If we look at the second equation, on the left we have x1 tilde is equal to, on the right, arctangent of t0 tilde. All right, and so you see that what we have now is quite expected. We have one equation here involving x0 and t0. We have a second equation here that could have possibly involved x0 and t0, but that's even much simpler, right? Because this one is already solved. So x0 tilde is pi times k tilde, which is nothing but, I would just reintroduce k, right? Pi k times epsilon. We can substitute to the equation here in order to get t0. T0 tilde is 1 over x0 tilde, which is 1 over pi k epsilon. And then what do we have? We have a second equation here, which gives, in combination with this one, should provide two equations with two unknowns, x1 and t1, but you see that this one is already solved for x1. So we have x1 is arctangent of t0, so 1 over pi k epsilon. And if you wish, you could express t1, but this is something that is probably not useful in this case, all right? Because what we are interested in at the end of the day is to write the sequence for x. Remember, we wrote this is x tilde over epsilon. So this is x0 plus epsilon x1. So it means x0 over epsilon. X is equal to x0 over epsilon, so pi times k. And plus epsilon simplifies, so we just have arc tangent of 1 over pi k epsilon. This is a large root, and additionally to this, we have terms that are plus order epsilon square divided by epsilon All right, plus terms of order epsilon. All right, and this is a large root, so we should keep in mind that k over here is as soon as k is equal to, I don't know, probably 3, 4, 5 times pi. This is already more than 15, and we see that we already have something that is quite large for x. And actually the quality of those roots is something that is just amazing if you compare them to numerical approaches. All right, and what is also interesting to consider at the end is that as k grows very large, so if you look at the limit for k going to infinity of the arctangent of 1 over pi k epsilon, this is the arctangent of 0, it means this is 0. And so this also means that if you look at the large roots, we could actually observe that they are located exactly over here, where the tangent, in fact, is equal to 0, and not any longer where it is singular. All right, so I hope this was clear. So you see that in this exercise, we used two different approaches. One for the small roots was possible because we could expand, we could just get rid of the singularity. That's what we did here. There's a singularity. We could get rid of it just by multiplying on the left and right by the cosine. And then we could expand the sine and the cosine, which are regular functions of their arguments. And that could provide us with a simple and usual asymptotic expansion for the small root. Concerning the large root here, we couldn't do this because the form of the nonlinearity corresponding to the trigonometric expression was a little bit more complicated. And so we used a trick. The trick consisted in adding a second quantity, a second variable here. Just write two problems, two equations, solve them simultaneously, and we could get the expansions for both x and t. I didn't write the expansion for t because this one is less interesting here, since we are interested in solving the problem just for x. All right, I hope it was clear and you could get it, and you'll be able just to apply the same techniques on your own on other problems. All right, so thanks a lot for listening and keep going.